All right. So today's topic is what is matter, and we're going to focus on solids. All right. Let's get started. So, a real quick review. What is the definition of matter? Anybody? What is the definition of matter? We should know this. All right. You're the first hand I saw. Not weight, but mass. Exactly. Okay. So, anything that has mass and takes up space. All right. So you don't need to write that down. That's something you already know. If you don't know that, that's something to make sure uh, that you do know. Okay. So examples would be the sun, the earth, tables, books, air, helium. All right. The air around you. Okay. The air around you is mass. All right. It has matter. You can feel the particles when you move your hand around like this. All right. So those things are all considered to be matter. And we should remember particle theory. All right. Particle theory is that all matter is made up of tiny particles, and those particles are doing what? They're what? They're in motion. Okay, very good. Okay, so they are in motion. If you remember this, this is a picture. What are these little spheres? Those are atoms. Okay, so this is an electron microscope picture of actual atoms. All right, and you might remember the world's smallest movie, The Boy and His Atom. Hopefully, you remember that. All right, so we know that particle theory is that all matter is made of tiny particles, and number two, those particles are in motion. So that's good. Now, there are three familiar states of matter, and this is something you know. This shouldn't be something where you're like, oh my gosh, solid. I've never heard of that today. Okay. All right. And I'm sure you guys are familiar with these three states of matter. There are more than these three states of matter, but in elementary school, you learned this, and they were what? Yes, Michael. Solid, liquid, gas. Okay. So we are familiar with that. So solid, liquid, gas. We are familiar with that. Okay. And another name, here's our first note we're going to be writing down. Another name for states of matter. It's a synonym. Okay, so it's synonymous would be phases of matter. So you can either say states of matter or phases of matter. Either one is the same thing. So let's get a definition for solid. A solid is defined as matter that has a definite shape. Has a definite shape. Consider the following. If I have a brick in a box, right? So there's a beautiful drawing of a brick in a box, and you're going to be amazed by this animation. All right, so what if I take this brick out of the box? Okay, has the brick changed its shape? No. Okay, so it doesn't matter what container it's in. If it's in the box, if it's outside the box, it's shaped like a brick. Okay, it hasn't changed its shape. All right, so like, again, that shouldn't be shocking to you, I hope. All right, so even if you remove a solid from its container, the solid does not change its shape. What if I put the brick in a different shaped container? So if I take it from a rectangular shaped container and I put it in a hat box, okay, did it change its shape? Is it magically changed into a duck or something? No, it's still brick. All right, it's still the same shape. So it doesn't matter, again, what container it's in. If it's inside the container, outside the container, if it's in a round container, doesn't matter. Okay, it's the same shape. A solid does not change its shape based on the shape of its container. And yes, just seeing if you're paying attention. That's good. That's good you observed that. So I don't know how many of you guys saw the smiley faces. Do you guys see the smiley face? All right, but you did. So that's good. That was actually kind of a little, not a test, but a little check for observation. So that's good you observed. And if you remember at the beginning of the year when we talked about scientific method, if you see something weird, question it, which you did. So good job. All right. A solid does not change its shape based on the shape of its container. The second part of the definition for solid is that it has a definite volume. It has a definite volume. And hopefully you remember what the word volume means. It's been a while. What does the word volume mean? Uh, that would probably be area of a triangle. One half base times height would be like the area of a triangle. Length times width would be like an area of a square or a. Okay, yeah, that's fine. So the formula for volume would be length times width times height, but the definition would be what? It's the amount of what? It's part of the definition of matter. Okay, very good. So the amount of space in an object is its volume. So this brick Does it take up more space if it's inside the box or if it's outside the box? Which one does it take up more space? The same. Okay, so it's the same. It doesn't matter. It's the same volume. So if this is 500 milliliters, this is 500 milliliters of volume. It's the same thing. The brick doesn't matter if it's inside or outside the container with the amount of space it takes. All right, a solid does not change its volume depending on the size of the container. How do the particles in a solid behave? All right, well, if we were to take a look at particles in a solid, again, another amazing animation. So if we focus in on the brick particles, what do we notice? Well, okay, what are those particles doing? Well, they are doing this. They are closely packed together, first of all. So they're located relatively close to one another. Okay, they are packed closely together and they are vibrating. So they're moving around kind of like this, but they're staying in place. Because according to particle theory, all matter is made out of particles, and those particles are in motion. So they are in motion, they're moving, but they're staying in place. Okay, that's what this drawing is kind of giving. There's little wobbly lines there. So those particles are kind of wiggling around. This is important. Particle A and particle B do not change places. Particle A stays here. Particle B stays here relative to each other. All right, so on your desk, the particle here on your desk does not all of a sudden move over there. If it did, your desk would change its shape. Okay, your desk does not do that. That's probably a good thing. All right, so in this case, if the particles moved, the brick would change its shape. Doesn't happen. All right, here's a little animation of this. Same. You might even want to double star this. This is kind of a key point. One of the important things about these next lecture series, and probably a little bit different than what you learned in elementary school, is that we want to think about this in terms of energy. A lot of thought about energy. Solid particles do not have enough energy to change position. And again, you might want to, like I said, double star that. That's really a key point. A good analogy. Do you guys know what an analogy is? You guys know what that term is? It's kind of like a comparison. All right, a good analogy to the way particles act in a solid would be kind of the way you guys are acting right now. So if you look around at each other, at one another, and are you guys moving? Are you in motion at all? I mean, I'm looking around, okay, swinging her foot, kind of, swinging, putting her arm back and forth, kind of like this, rocking back and forth, all right, crossing, uncrossing your legs. Those things, you are in motion, okay? But what are you not doing? Moving? That's right. You're in motion, but you're not moving different positions, okay? You're not getting up and walking across the room. That would be different, okay? Everybody can move around like this as much as you want. Like the teacher says, hey, sit in your seat. Well, I am, haha, teacher. All right, so you can sit around, move around, wiggle around as much as you want, but you're not changing position. That would be like a solid. So the more you're wiggling around, the more energy the solid has, but you still don't have enough energy to get up and walk across the room. Okay, does that make sense? All right, so you can do that. So two basic types of solids. We have a crystalline solid. Now this word you might not be familiar with, but there's a word in there you probably are familiar with, which is what? Crystal. All right, so just kind of picture in your mind, if I said to imagine what a crystal looks like, I'm sure you probably have an idea. A crystalline solid. What a crystalline solid looks like is that it has particles arranged in a repeating pattern, repeating three-dimensional pattern, and it's called a crystal. So in this case on the screen, you see this is sodium chloride, where you have a sodium and you have a chlorine. You have a sodium and a chlorine, a sodium and a chlorine. Do you see a repeating pattern here? Sodium, chlorine, okay? So that is a repeating pattern, and it is in a crystalline shape. Do all solids look like this? Do all solids have a repeating crystalline shape? All right, you might be able to think of some, but certainly not everything. I will. I'll have to find out. Now, some of the characteristics of a crystalline solid is that they have flat, smooth sides, and they have sharp angles. All right, think about if you've ever seen like somebody's diamond ring. Okay, that is a crystal. All right, so a diamond, table salt. oddly enough. Snowflakes, these are all crystalline solids. So go ahead and write that down. So here are 3 examples of crystalline solids: diamonds, table salt, snowflakes. All right, so here's some pictures of some crystalline solids. In this case, it's a snowflake. Depending on the temperature of the air, snowflakes will form different shaped crystals. So, like for example, some snowflake crystals are just kind of like a rod. I should have had a picture of that. I don't know where it went. But here's a clip of crystals forming. Here we go. This might be something that you've done in schools. Have you ever done anything like this with like Epsom salts? You guys ever done this? All right. So you can make little crystals that grow. Yeah, it does look like candy. If you've ever made rock candy, like sugar from sugar solution. Okay, a second kind of solid is what's known as an amorphous solid. This one you probably have never heard of before. An amorphous solid. Do you see any roots in that word that you recognize though? Like morph? Yeah, morph, exactly. All right, so morph is a part of speech you probably recognize maybe. All right, so an amorphous solid. Remember, crystalline solid particles are arranged in a repeating pattern. So this is a crystalline solid. It looks very nice and neat and pleasant. Okay, an amorphous solid, the particles are not arranged in a repeating crystalline pattern. They're randomly arranged. All right, so it is a random arrangement, kind of like if you take a whole bunch of grains of sand and throw them together in a cup. The particles are not going to be arranged in any repeating pattern. It's called an amorphous solid. Amorphous solid. All right, here's some examples of amorphous solids. Some examples of amorphous solids would be rubber, okay, like a rubber ducky. And if you've had music, you've probably seen a lot of these in somebody's classroom, right? Okay, rubber is an amorphous solid. Here's a clip. Okay, you guys have probably seen something like that before. You guys have played with the thinking putty. Okay, that was an amorphous solid. Here's another clip showing putty. Is it a solid or is it a liquid? Candle wax. Candle wax is a really good example of an amorphous solid also. Okay, some other examples. We had rubber as an example, wax as an example. Plastics are an example. And I put chewing gum along with this. Any ideas why? Why did I put plastics and chewing gum? Yes, Ryan. Yeah, exactly. Surprisingly, to a lot of people, chewing gum is made out of plastic. Sounds delicious, right? How many people have heard the thing about how chewing gum takes 7 years to get for you to digest? Have you guys heard that? Yeah, yeah, that's not true. I mean, it'll pass through you. Here's a clip. This is pretty neat. Hold on, I'm gonna turn my audio off. Hopefully maybe that'll help.
Chewing gum dates back to the ancient Greeks who chewed resin from trees. Modern chewing gum was patented in the U.S. in 1869 by, believe it or not, a dentist. In 1928, another American invented bubble gum. Bubble gum comes in gumballs of all colors and sizes. But for blowing bubbles, nothing beats the chewy, gooey pink stuff in the twist wrap. It all starts with the gum base, the stuff that makes gum chewy. Traditionally, the base came from tree resin. Today, it's synthetic, made of plastics and rubbers. They pour the gum base into a mixer, then add color and flavoring. As it begins mixing, they pour in glucose syrup, a sweetener. Because it's liquid, it helps keep the gum base soft. Next, they add dextrose, a powdered sweetener. They blend the ingredients for about 20 minutes. The stirring action builds up heat, which melts everything together. The mixture's ready when it reaches the consistency of bread dough. They transfer it by cart to a machine called the pre-extruder. The machine squeezes the mixture through a narrow opening, like squeezing toothpaste from the tube. This transforms the big, bulky wad into thin, manageable strips that can then go through the extruders. The extruders squeeze each strip down to the actual width of a piece of bubble gum. It comes out as one long continuous stream to be cut into bite-sized pieces later on. This extrusion process heats up the gum. If they were to cut and wrap it now, it would stick to the wrapper. So the next stop is a cooling chamber. The gum goes in for 15 minutes at temperatures between 37 and 45 degrees Fahrenheit. When the bubble gum comes out, it's cooled down enough for what they call the cut and wrap. One machine does both jobs in a fraction of a second. Watch the action in slow motion. As the continuous stream of gum enters on one end, the machine cuts it into bite-sized pieces, pushes each piece into a wax paper wrapper, then twists both ends of the wrapper closed. Here's the slow motion replay from a different angle. The machine processes 900 pieces of bubble gum per minute. Last stop, packaging. The bubble gum moves onto a scale that automatically weighs out the right amount per tub. They seal the tub with plastic to make it airtight. This keeps the bubble gum fresh. Ever wonder why bubble gum is pink? It's because that's the only color Walter Deemer had on hand when he invented this treat back in 1928. Since then, the color just stuck.
That's pretty neat. I like that clip. All right, hopefully you enjoyed that clip as much as I did. And then this one, this is kind of like a bonus clip, because in the past I've had somebody say, hey, that kind of reminds me of this. All right, let's take a look at this one. This is kind of a similar idea.
Candy canes come in many different colors and sizes. Candy makers start by cooking up a big batch of sugar, water, and corn syrup. Next, they prepare a mix of starch and peppermint flavoring. As they blend together, the flavoring binds to the starch. The flavoring mix is emptied into the middle of the syrupy slab. Then the whole thing is fed into a machine that folds the batch repeatedly, using shovels and a plunger. This distributes the flavoring evenly. Cold water is piped into the shovels and the kneading table to cool the candy cane mix, so it takes on a stiffer consistency, which is needed for the next step, the automated pullers. These pullers stretch the mixture around a metal post. This action aerates the candy, turning it white. This batch will make 3,200 candy canes, but there's still a lot more work to do. The candy is rolled into a fat log as heaters warm it until it's pliable enough to shape. Next, they roll strips of red-colored candy. A worker stretches and folds it to widen the strip. Two of the red strips are arranged on either side of the white candy. The block of candy weighs 100 pounds, so it takes 2 workers to transfer it to a batch roller. The batch roller cylinders roll the candy thinner and thinner, dramatically reducing the log's diameter until it reaches candy cane dimensions. A torch moves across the candy to keep it pliable. The sugary batch travels between wheels that slim it down even more. The rope of candy moves forward in a wave-like fashion. This gives it some slack so it doesn't stretch as it moves through the next set of wheels. The candy rope moves through 2 angled belts that twist it, and a chain of knives cut the twisted rope to candy cane size. This production has been perfectly choreographed. Here, a roll of cellophane unwinds, and a device wraps it around the candy sticks. A blast of hot air shrinks the cellophane on the ends of the canes. Now it's time for these candy sticks to get their signature crooks. This machine, called a crooker deck, bends the ends. An overhead bracket brush gently secures the canes, because though they're pliable enough to bend, they're still fragile. There's a camera inside this robotic arm that spots the candy canes on the conveyor belt, before the arm picks them up 2 at a time. It places them in cardboard packages by the dozen. It takes about a half hour to make a box of candy canes, but they're sure to come to a very sticky end in less time.